In this video, I'm going to be going over the recitation packet for Dr. Collini's Chem 2380 class. We're going to be covering the reactions with aromatic molecules, directing effects, and reactions of ketones and aldehydes. Question 1. What reagents and in what order would you accomplish the following transformation? So we start with the benzene, and our end product has a tert-butyl group and a nitro group. So the first thing that I would do is determine if each of the substituents are activating or deactivating and what their directing effects are, and that will help us to know what order to do the reaction. So the tert-butyl group is an electron donating group, and it directs orthopara. So I'm going to write that here. And the nitro group is an electron withdrawing group because both induction and resonance are going to pull electron density away from the ring. So it's going to be deactivating, and it is meta. So now we look at the positioning relative to each other, and you can see that these two substituents are para to each other, which means that we must have added the tert-butyl group first, so that once the tert-butyl is added, it will direct to the para position. If we were to do it backwards, the nitro group added first, then the tert-butyl group would be added in the meta position, and that's not what we want. So we know that first we need to add the tert-butyl, and second we need to add the nitro. And the reagents to do that are, number 1, for tert-butyl, we need to have some sort of alkyl halide. So I'm going to do this tert-butyl chloride with AlCl3. And when that reacts, it's going to add the tert-butyl group. And then once the tert-butyl group is there, to add the nitro group, we use HNO3 with sulfuric acid, H2SO4. All right, moving on to part B. Again, we have a benzene, and this time our substituents are a bromine and a tert-butyl group. So again, I'm going to label them as I did before. So the bromine is an electron withdrawing group because even though it is capable of resonating electron density into the ring, in this case the induction effect is stronger, so it's going to be overall a withdrawing group. But it is the exception to the directing effects rule. If it's any of the halogens, they are going to direct orthopara, and that's because of their minor resonance contributors. If you were to resonate the lone pairs on the bromine into the ring, you would see that the lone pairs end up in the ortho and para positions, which make it an orthopara director. And then the tert-butyl group, same as before. Is an electron donating group, and it directs orthopara. So because these both direct orthopara, you might be inclined to think that it doesn't matter which order you put the two substituents on, and to some degree you'd be correct. If you did the bromine first, it would still put it in para, and if you did the tert-butyl group first, it would still put the bromine in para. But the difference here is the withdrawing versus the donating. If you have the option to do a donating group first, you should do that because it will improve your overall yield of your final product, because electron withdrawing groups tend to have lower yields. They're not as effective at pushing that reaction forward. So if you can do something to make the reaction go more to the direction that you want it to, you should do that substituent first. So in this case, we'll do the tert-butyl group as step 1, and then the bromine as step 2. And the reagents for that, again, for tert-butyl, it's going to be the same as part A. I'm going to do this tert-butyl chloride and AlCl3. And then step 2, to add a bromine, I will use Br2 and FeBr3. Okay, part C. In this one we have another bromine and a, 1, 2, 3, 4 butyl group. So again, the bromine is a withdrawing and it's orthopara. And the butyl group is an electron donating, and it's also orthopara. But we see that the positions of the two substituents are meta relative to one another. So that means that there must have been some sort of directing effect that allowed these two substituents to add meta. And the way that we can accomplish that is by having something that is meta-directing initially and then changing it into our final product. So what I mean by that is we could get rid of all of this. Let's imagine that we had this ketone here instead of just the butyl group. If this were our product, it would be an electron withdrawing group and it would be a meta-director. So in that case, if we added that substituent first and then added the bromine would add meta. And then once the bromine is added, we could do something to this molecule to make it into our final product, which would just be the bromine, or the bromine and the butyl. So how do we get rid of that carbonyl group? We learned a reaction that gets rid of carbonyls and leaves behind just the carbon chain. And to do that, it's zinc and mercury in the presence of HCl. So that will be our final step here. Zinc, mercury, and HCl. So that will be our last step, but we still need to figure out the previous steps. So again, we have to add the carbonyl carbon first because that's our meta-director. So step 1 is to add the carbonyl carbon, and we can do that using a Friedel-Crafts. So I'll use this acyl chloride. This is a Cl group. So when the benzene attacks it, the chlorine leaves and you're left with the ketone with 4 carbons as shown. And again, we need AlCl3 to help accomplish that. And then step 2 is adding our bromine, which again is just Br2 and FeBr3. Okay, and then step 3, as we mentioned before, once you've added your bromine, we get rid of the carbonyl carbon, and we do that using zinc, mercury, and HCl. Okay, question 2. For each of the molecules below, where would the new electrophile add if going through an electrophilic aromatic substitution? So this is just thinking about directing effects again and the impacts of multiple substituents on the overall addition of the molecule. So for question A, or part A, we have 2 nitro groups and 1 methyl group. So let's go through each of these substituents and think about where a substituent would add based on each of the individual directing effects. So for this nitro group, nitro is a withdrawing group and it directs meta. So the meta position relative to the nitro group would be here and here. But that second position already has a substituent, so we know that a new substituent could not be added there, which means that that bottom carbon is the only place that the nitro group could direct to. This methyl group is an electron donating group and it directs orthopara. So the ortho positions relative to the methyl are already filled out by the nitros, so those are not available. The para position is available. So currently we have 2, the nitro and the methyl are both directing to that bottom carbon. And then let's check this last nitro group. Again, nitro is withdrawing, it's a meta director. This meta position is already taken, so the only meta position that's available is this bottom one. So in this case, all 3 substituents are directing to that bottom carbon. So that's where a substituent would add if we had a reaction going on with this molecule. So if we had some reaction with an electrophile, the electrophile would add to this position. Okay, for the second example, we have 2 methyl groups and a cyano group. So let's again go one by one. This methyl group is an electron donating group and it directs orthopara. So the ortho position here is already filled, but we could direct ortho here or para here. The cyano group is a meta director, and it's going to direct meta here or meta here. And then this methyl group, again, is an orthopara director. This para position is already filled, so it could direct here or here. So all three substituents are pointing towards the same two positions, and you'll notice that this molecule is symmetric, so those two positions are equivalent, so it would add to either one of those sides. So let's draw that. If you had an electrophile, you could either get this product or this product. Question 3. Draw the mechanism and predict the product of the reaction. Label the electrophile and the nucleophile. So this is getting into reviews of Grignard reagents and reactions. We have a carbonyl carbon and ethyl magnesium bromide, which is basically the equivalent of just CH3CH2-. So I'm going to draw that. Just imagine that there's like a carbanion that's going to act as a nucleophile. And it's going to attack at the most electrophilic position, which in this case is the alpha carbon here, and it's electrophilic because we have a partial positive or partial negative on the oxygen, partial positive here when this double bond moves up onto the oxygen. So because of that partial positive, the alpha carbon is electrophilic, meaning that Grignard is going to attack here and bump those electrons up onto the oxygen. And when we do that, the product is going to look like this. And then the second step is to add acid. So when we have H3O+, the negative charge on the oxygen is going to be able to do an acid-base reaction, steal that, and become an alcohol. So that's the Grignard reaction. It does ask us to label our nucleophile and electrophile. So again, this is the electrophile, because it's the thing that is being attacked. And this is our nucleophile. Question 4, name or draw the following molecules. So this first one, let's find the longest carbon chain. So we could start here, we could start here, we could start here. It looks like this is going to be our longest, 1, 2, 3, 4, 5, 6, 9. If you were to do it starting here, you'd have 1, 2, 3, 4, 5, 6, 7, 8. So we're going to start with the yellow. However, in order to name it in the proper direction, we need to put the carbonated carbon on the lowest possible number. So we're going to name it this direction, 1, 2, 3, 4, 5, 6, 7, 8, 9. So the parent chain is going to be non-ane. And then our substituents, we have a methyl group. So that's going to be 1, 2, 3, 4, 4 dimethyl. We have this ethyl group coming off of carbon 1, 2, 3, 4, 5, 6. And we have the carbonyl carbon, which is on carbon 1, 2, 3. And since ketone is the highest priority, it's going to get the suffix. So we're going to do 3-one at the very end of our name. So this is a suffix. The other two are prefixes. And to name the prefixes, we just put them in alphabetical order. So ethyl comes before methyl. So the full name is going to be 6-ethyl 4,4 dimethyl non-ane, drop the E, 3-one. If you happen to look at the key that Dr. Collini posts on Canvas, she numbered this direction, so her naming looks a little bit different, but I think that was just a mistake because the longest parent chain is 9, not 8. I forgot to mention this when I was doing my screen recording, so I'm jumping in now to also mention that this molecule does have stereochemistry. The carbon at position 6 is chiral, so if you wanted to figure out R or S, you could assign priorities. In this case, the chain with the carbonyl is position 1, the propyl group would be priority 2, and the ethyl group is priority 3. So moving from 1, 2 to 3, that's a clockwise direction, so this molecule would be R. Okay, part B, this time we're working backwards, so we have a written name that we need to draw the corresponding structure. So the first thing I like to do is find the parent chain. So the parent chain for this one is cyclohexane-one. And since there's no number before the one, we know that it's a ring, the cyclohexanone, the carbonyl carbon is going to be at position 1. So the parent chain is a 6-membered ring with a carbonyl at position 1. And we know that that's position 1 because it's a ketone with no other higher priority groups. Goodness. So that's position 1. If we were to label the rest of the positions, 1, 2, 3, 4, 5, and 6, we have 2 bromines on carbon 3 and an ethyl group on carbon 4. So on carbon 3, we have dibromo, and on carbon 4, we have an ethyl. And then we do have stereochemistry, so in this case, we have S, so this will either be on a wedge or a dash. In order for it to be S configuration, let's figure out priorities. This one will have priority 1 because it's a carbon with 2 bromines. This will have priority 2 because it's a carbon connected to the longer carbon chain. And this will have priority 3 because it's the shortest carbon chain, and then 4 is the invisible hydrogen. So if this is 1, 2, 3, that is S if the ethyl group is on a wedge. So we're going to put it on a wedge in order for the stereochemistry to be accurate. Oops. Okay, so if that's on a wedge, then the stereochemistry is what it needs to be. Question 5 asks us to explain why the alpha carbon of a carbonyl is a good electrophile. So I think it's easiest to explain with a picture. The carbonyl carbon ends up being a good electrophile because of resonance, because that double bond is capable of resonating up onto the oxygen, which puts a negative charge on the oxygen and a positive charge on the carbonyl carbon. So because it has that slight partial positive, it's going to be more electrophilic than basically anything else on that molecule. And this says part C, but it's just part A of 5. Are aldehydes or ketones better electrophiles? Explain your reasoning. So if again, if I were to draw both of these out, let's do just the simplest ketone versus the simplest aldehyde. When we compare both the steric and the electronic effects, we'll find that aldehydes end up being better. And the reasoning for that is because when a nucleophile tries to come in and attack, there's more space over here because you're only dealing with these two little hydrogens. So it's easier to get in and attack at this position versus coming over here. These CH3 groups are much bigger, and so it's more difficult for the nucleophile. From like a space-wise perspective, it's more difficult to get in there and attack. So sterically, aldehydes are better. But also electronically, if we think about induction, the hydrogens, again, those are just lone protons. They're not capable of inductively giving any extra electron density to the alpha carbon. So this position is not able to be supported by the hydrogens. Whereas over here we have these CH3 groups, they're able to push just a little bit of their electron density onto that alpha carbon position, and they're able to help stabilize the positive. And again, more stable means less reactive. So again, aldehydes are going to be the better electrophiles because they're more reactive in the sense that they are less stable. So just to put that into writing, aldehydes are better electrophiles because less sterics, and less inductive stabilization. And that is the end of this packet. If you have any questions about what I've done here, feel free to reach out and let me know.